Exponential growth. In this video, you'll learn how to explain the connections between an equation and a graph that represents exponential growth. You'll also learn how to write and interpret an equation that represents exponential growth. So an exponential function is written as y is equal to a times b to the x power, where a tells us our initial amount and b tells us the growth factor. X will tell us the number of time intervals, and y will let us know the final quantity. Let's practice by writing an exponential equation that represents a bank account that starts with $1,000 and doubles every year. So we'll start with an exponential function, and we'll replace a and b with what the story tells us. A is going to represent the initial amount, and b is our growth factor. We can see that the account starts with $1,000, so we'll replace a with 1,000. And we know that it doubles every year, so we'll replace b with 2, and now we have an equation to represent this situation. Let's look at a couple more examples. In a biology lab, 500 bacteria reproduce by splitting. Every hour, each bacterium splits into 2. So we'll use this story to fill out this table where we're given the number of hours. When the hour is 0, that gives us the initial amount, which was 500 bacteria. After 1 hour, we'll double our amount, which gives us 1,000. And then after 2 hours, we'll double again, giving us 2,000. And then after 3 hours, doubling 2,000 will give us 4,000. Now we need to look at hour 6. So we need to double 3 more times since we skipped 4 and 5. So we'll have an answer of 32,000 bacteria after 6 hours. Now let's write an equation using this table. So we know the initial value is 500, so A will become 500, and B is going to represent our growth pattern. Since we were doubling every time, our B value will become 2. In a different biology lab, a population of single-cell parasites also reproduces hourly. An equation that gives the number of parasites P after T hours is P equals 100 times 3 to the T power. We're going to explain what the 103 mean in this situation. So we know that every exponential function can be written as y equals a times b to the x power, where a is the initial amount and b is the growth factor. So if we take the equation that they gave us of b equals 100 times 3 to the t power, then we can see that we have an initial amount of 100 and the growth factor is 3, so this is tripling. In this example, we want to find the value of 4 to the 0 power times 4 to the second power. So let's take the expression they gave us. 4 to the 0 power will give us 1, because anything to the 0 power is always 1. And 4 squared is 16. Multiplying 1 times 16, which gives us a final value of 16. We can also apply one of the exponential properties that says if we have the same base, which in this case is 4, then we can just add the exponents. So we'll keep the base of 4, and adding the exponents gives us an exponent of 2, and 4 squared would give us the 16 that we already found. Let's look at a few more exponential properties. So we'll start with the power of products. So if we're multiplying 2 powers and the bases are the same, then we can add the exponents. So we would keep the base of 4, and adding 2 plus 3 would give us an exponent of 5. If we look at another example where the base is now 6, then we can multiply by adding the exponents. So we'll keep the base of 6, and adding negative 2 plus 6 gives us an exponent of 4. Now let's look at the power of quotients. So if we have an example like 4 to the 8th divided by 4 to the 2nd where the bases match, then we can just subtract the exponents. So we'll keep our base of 4, and 8 minus 2 will give us an exponent of 6. Or if we have 7 to the 5th divided by 7 to the 3rd, then we'll keep our base of 7, and subtracting 5 minus 3 will give us a new exponent of 2. Now let's look at power of powers. So if we have 4 to the 3rd all raised to the second power, then we can keep the base and multiply the exponents. So we would have an exponent of 6. Or if we had 5 to the negative 1st all raised to the power of 8, then we would keep our base of 5, and multiplying negative 1 times 8 would give us negative 8. This brings us to our last property of negative powers. So if we take the example that we were given of 5 to the negative 8th, then we're going to rewrite this as a positive exponent by putting it on the bottom of a fraction under 1. So if we had another example like 4 to the negative second, then we can make the exponent positive by putting it under 1. Let's look at some more examples of using these exponential properties. Which expressions below are equivalent to 3 to the 8th power? So let's start by finding out what 3 to the 8th power is. If we multiply 3 times itself 8 times, we'll get a value of 6,561. So we'll see which of the following expressions also give us an answer of 6,561. If we look at 8 cubed, we'll do 8 times 8 times 8, which gives us a value of 512. So this is not equivalent. Now let's look at 3 over 10 divided by 3 to the second. Using the division property of exponents tells us to keep the base of 3 and subtract the exponents, which would give us 3 to the 8th. Since this matches what we were given, this one is equivalent. Now let's look at 3 times 8. This gives us a value of 24. So this one's not equivalent. Now let's look at 3 to the 4th, all raised to the second power. The property of power says that we can keep the base of 3 and then multiply our exponents. So we'll have a new exponent of 8, and this matches what we were given. So this one is equivalent. Now we have 3 times 3 to the 4th power. Multiplying the parentheses first will give us 9 to the 4th power. And multiplying 9 times 9 times 9 times 9 gives us a value of 6,561. So this one is equivalent. Even though the powers didn't match exactly up with what we were given, it still gave us the same value. Now let's look at the last one, which is 1 over 3 to the negative 8th. So to make a negative exponent positive, we need to switch where it is on the fraction. So now we'll put 3 to the 8th on top of the 1, which just simplifies to 3 to the 8th power, and this matches what we were given. So this one is also equivalent. In this example, a bee population is measured each week and the results are plotted on the graph. We can see the x-axis represents the number of weeks and the y-axis represents the bee population. What is the bee population when it is first measured? So this is represented by the y-intercept when x is 0. So we can see that there were 500 bees when it was first measured. Is the population growing by the same factor each week? So we'll look at each interval and decide how much it's going up to see the factor that it's growing by each week. Between the values when the x is 0 and 1, it went from 500 to 100. Between the values of 1 to 2 weeks, it went from 1,000 to 2,000. And then in the last interval of 2 to 3 weeks, it started at 2,000 and went up to 4,000. So it looks like in each interval, the population was doubling every week. Now let's write an equation that models the bee population given the number of weeks. So we'll take our exponential function, where a is our initial value and b is our growth factor. We know that a was represented by the 500 bees we started with, and b is going to be 2 since it was doubling each week. Now we have an equation for this graph. Now we have a savings bond that is initially bought for $250. It doubles in value every decade. We're going to complete the table representing this situation. The dollar value after 0 decades since bought would just be the $250 that we started with. To find the value after 1 decade, we'll take the $250 and multiply it by 2 since we're doubling, which will give us a value of $500. And then we'll double this again to find the value after 2 decades. So we'll get $1,000. And then we'll double this again to find the value after 3 decades. So we get $2,000. Now to find the value after d decades, we want to write an expression that will find the value after any amount of decades given. So we're going to take the $250 that we started with and multiply by our growth factor of 2, and our exponent will be d, representing the decades that were given. How many decades does it take before the bond is worth more than $10,000? So we know that after 3 decades it was worth $2,000. So 4 decades would be $4,000, 5 decades would be $8,000, and 6 decades would be $16,000. So this will happen a little bit more after 5 decades. Now let's recap what we've learned. In relationships where the change is exponential, a quantity is repeatedly multiplied by the same amount. The multiplier is called the growth factor. We use the exponential function y equals a times b to the x power to model these situations. where A is the initial amount and B is the growth rate.